Welcome back. The specific objectives of this particular lecture are to classify refrigerant condensers, discuss salient features of various types of refrigerant condensers, define heat rejection ratio and present expressions for heat rejection ratio and mean temperature difference. At the end of the lecture, you should be able to classify refrigerant condensers based on the external fluid, type of construction, etc. Describe salient features of various types of condensers and evaluate heat rejection ratio and log mean temperature difference LMTD of refrigerant condensers. Let me give a brief introduction here. As you know, condensers and evaporators are heat exchangers in which the refrigerant undergoes a phase change. In condensers, the refrigerant vapor condenses by rejecting heat to an external fluid which acts as a heat sink. Condenser is an important component of any cyclic refrigeration system, and proper design or selection of condenser is essential for good system performance. In a typical refrigerant condenser, the refrigerant enters the condenser in a superheated state. It is first desuperheated and then condensed by rejecting heat to an external medium. Temperature of a pure refrigerant remains constant during condensation when the refrigerant side pressure drop is negligible. The refrigerant may leave the condenser as a saturated or a subcooled liquid depending upon the temperature of the external medium. Now, let me show the picture. You can see here the refrigeration cycle on TS diagram. Here the condensation process is shown by 3-3, and the heat rejection in the condenser is shown by the process 2-4. This heat rejection consists of 3 different stages. The first stage, that is 2 to 3- is what is known as your desuperheating zone, and during which the pressure remains constant, but the temperature varies from T2 to T3-, which is nothing but the saturated temperature corresponding to the condenser pressure. And next stage is 3-3, which is nothing but the condensation phase, during which both the temperature as well as the pressure of the refrigerant remain constant. Next you have the stage 3 to 4, which is a subcooling zone, during which again the pressure remains constant, but the temperature decreases from T3 to T4. And in this picture you can also see the temperature profile of the external fluid. So, here it is external fluid flows in an opposite direction, that means it is a counter flow type of condenser. So, as the external fluid flows through the condenser, its temperature increases because it takes the heat from the condensing refrigerant. Okay. Now, the external fluid in most of the refrigerant systems, the external fluid does not undergo any phase change. Okay, that means the heat transfer of as far as the external fluid is concerned is sensible. Its temperature only increases, but it does not undergo any phase change. But there are some special applications such as in cascade refrigerant systems where the external fluid also undergoes a phase change, right. But our discussion in this particular lecture is limited to an external fluid which does not undergo any phase change. Okay. Now, let us look at the classification of condensers. Based on the external fluid, condensers can be classified as air cooled condensers, water cooled condensers and evaporative condensers. Now, let us look at each of these. First, let us look at air cooled condenser. As the name implies, in an air cooled condenser, air is the external fluid. That means the refrigerant rejects heat to air flowing over the condenser. Air cooled condensers can be further classified into natural convection type or forced convection type. Now, let us look at natural convection type air cooled condenser. Here the heat transfer from the condenser is by buoyancy induced natural convection and also by radiation. Since the flow rate of air is small due to the buoyancy and the radiation heat transfer is also not very high, the combined heat transfer coefficient of this kind of condensers is small. As a result, you find that a relatively large condensing surface area is required to reject a given amount of heat. Hence, these are used mainly for small capacity refrigerant systems such as household refrigerators and freezers. The natural convection type condensers are either plate surface type or fin tube type. That means, based on the construction, you can again classify the natural convection type condensers as plate surface type or fin tube type. In plate surface type condensers, these are mainly used in small refrigerators and freezers. The refrigerant carrying tubes are attached to the outer walls of the cabinet. The whole body of the refrigerator or freezer except the door acts like a fin, and insulation is provided between the outer and inner covers of the refrigerator. Hence, the outer body is always warm. These condensers are also known as flat back condensers. Let me show a picture of this. This picture shows a typical plate surface type of a condenser used in a domestic refrigerator. You can see here that this is the refrigerator compartment where the food products are stored. Okay. So, this is the inner cover, normally made of plastic. This is the inner cover, and this is the outer cover, okay, normally made of a metal, okay, a metallic outer cover, and the space between the inner and outer cover is filled with insulation, normally a polyurethane foam, to reduce the heat leak from the outside to the refrigeration compartment. Okay. And now the condenser tubes or the refrigerant carrying tubes are attached to the outer cover. These are the refrigerant carrying tubes through which the refrigerant flows. Okay. So, as the refrigerant flows, it transfers heat first to the outer cover, and from the outer cover heat is transferred to the surrounding air. That means the heat transfer takes place finally from the complete body of the refrigerator, okay, to the surrounding air. Okay. So, since the condensing temperature is always higher than the surrounding temperature, you find that the outer surface of this kind of refrigerator is always warm. Okay. And this kind of condenser is also known as flat back type of condenser. One advantage claimed for this kind of a condenser is that since the outer surface is warm, there is no danger of water condensing on the outer surface. Okay. Now, let us look at fin type of condensers. The fin type of condensers are mounted either below the refrigerator at an angle or on the back side of the refrigerator. The fin spacing is kept large to minimize the effect of fouling by dust and to allow air to flow freely with little resistance. This is required because you are relying on buoyancy induced effect. In some designs, the condenser tubes are attached to a slotted plate which acts as a fin. And in another common design, thin wires are welded to the condenser tubing. This you must have seen in the older type of refrigerator. Let me show a picture of this. This is what is known as wire and tube type of condenser. Here you can see that the condenser tubing, the serpentine, this is the serpentine condenser tubing through which the refrigerant flows. Okay. For example, refrigerant enters at the bottom of the condenser, it flows through the tube, and as it flows through the tube, it rejects heat to the surroundings. Okay. Heat rejection takes place to the surroundings, and attached to these tubes are wires which are welded to these tubes. So, these wires provide additional area and they act as fins. So, heat transfer takes place not only from the refrigerant tubing, but also from these wires, and this whole assembly is kept at the back side of the domestic refrigerator. For all natural convection type of condensers, refrigerators should be placed such that air can flow freely over the condenser surface. So, you have to orient it properly so that proper airflow can be maintained. Now, let us look at forced convection type of air cooled condensers. In forced convection type condensers, the circulation of air over the condenser surface is maintained by using a fan or a blower. Okay, that means you use an external device for maintaining the airflow. These condensers normally use fins on air sides for good heat transfer. The fins can be either plate type or annular type. So, let me show the picture of a plate type of. So, this is what is known as plate, fin and tube type of condenser. So, here again you can see the tubes. Okay, these are the tubes through which refrigerant flows. Okay. And through to these tubes, plates are attached. These are the plates which are attached to these tubes. And if you see from the side view is something like this. You can see that this is the plate, okay, and these are the tubes through which the refrigerant flows. Okay. So, here if let us say that air also flows in this direction, okay, Then there are a number of rows in the airflow direction. For example, there are 3 tubes in the airflow direction, so you call this as 3 row type of condenser, and for each row there are 4 tubes. Okay, so this is what is known as your plate, fin and tube type of condenser. Next, this is annular fin type. That means you have again a tube through which refrigerant flows. Okay, and you also have an annular fin. Okay, so annular fin is attached to these tubes. So heat transfer takes place from the bare surface of the tube and also from the surface of the fin. Okay, so this kind of condenser is known as annular fin type of condenser. Forced convection type air cooled condensers are commonly used in window air conditioners, water coolers and packaged air conditioning plants. Forced convection condensers are either chassis mounted, so these are called as condensing units, or remote mounted. So what is a condensing unit? In a condensing unit, the compressor, induction motor, condenser with condenser fan, accumulator, high pressure, low pressure cutout switch and pressure gauges are mounted on a single chassis, and this complete unit is called as condensing unit of rated capacity. The components are matched to condense the required mass flow rate of the refrigerant to meet the rated cooling capacity. So this is known as a condensing unit. In fact, these condensing units are available off the shelf. That means if you want a condensing unit, let us say for a 3-ton refrigeration plant, then you can straight away buy a 3-ton refrigeration plant condensing unit, which consists of the compressor, condenser, the controls, motors, etc. So all that you have to do is you have to connect a suitable evaporator and expansion device to this condensing unit, so that you can have the complete system. Okay, so this is very advantageous in especially in smaller systems for quick assembly, because you do not have to match the components. That means match compressor with condenser, motor with the compressor, etc. That will be done by the manufacturer himself. Okay, so all that you have to do is you have to specify the refrigeration capacity and buy a suitable condensing unit, and then assemble the condensing unit with the evaporator and expansion device. Okay. Normally the air velocity varies between 2 meter per second to 3.5 meter per second for economic design, and the airflow rates vary between 12 to 20 meter cube per minute per ton of refrigeration. The area of the condenser seen from outside in the airflow direction is called as face area. The velocity at the face, also known as face velocity, is given by the volume flow rate divided by the face area. Face velocity is around 2 meter per second to 3.5 meter per second to limit pressure drop due to friction. The coils of the tubes I have already mentioned. The coils of the tube in the flow direction are called as rows, and a condenser may have 2 to 8 rows. The fins are usually of aluminum and tubes are made of copper, and fin spacing may vary from 3 to 7 fins per centimeter. For ammonia condenser, since ammonia is not compatible with copper, mild steel tubes are used with mild steel fins. Secondary surface area in all these forced convection type of evaporators or condensers, the secondary surface area, that is the surface area of the finned surfaces, is about 10 to 30 times that of the bare pipe area. Okay, so you get a large effective surface area. As a result, these type of condensers or evaporators are very compact and of lightweight. This is an advantage of the forced convection type of heat exchangers. Now let us look at water cooled type of condensers. In water cooled condensers, as the name implies, water is the external fluid, and depending upon the construction, water cooled condensers can be further classified into double pipe or tube in tube type, shell and coil type, and shell and tube type. Now let us look at double pipe or tube in tube type. These type of condensers are normally used up to 10 ton of capacity. In these condensers, the cold water flows through the inner tube while the refrigerant flows through the annulus. The refrigerant in the annulus rejects a part of its heat to the surroundings by free convection and radiation, and the heat transfer coefficient in these kind of condensers is typically low because of poor liquid refrigerant drainage if the tubes are long. Now let me show a picture of this double pipe type of condenser. This shows a typical double pipe type of a condenser which is formed in which is made in the form of a coil. Okay, so here you can see this is the inner tube, okay, through which the coolant flows, okay, and this is the outer tube, and the refrigerant flows through the space between the inner and outer tube, that means through the annular space. In this particular picture, the direction of the coolant and refrigerant are parallel, that means it is a parallel flow type. But in general you can also have counter current type, that means refrigerant enters from the top and coolant enters from the bottom, that means flow can be either counter current or co-current. Okay, and it is not necessary that you have to make this in the form of a coil, you can also have this in this form. Okay, so you can have tubing. Okay, let us say that you have the outer tube like this, okay, and the inner tube can be, the inner tube will be something like this, okay, and you can also have the many rows, that means you can have one row behind the other like that. As I was telling, in these type of condensers, the heat transfer coefficient is relatively low, because the refrigerant that is flowing here condenses, and we will see later that the heat transfer coefficient depends upon how fast the condensate drains out. So if the tube is very long, then the drainage takes place very inefficiently. As a result, you will find that the heat transfer coefficient on the refrigerant side is small. Now let us look at shell and coil type. These type of condensers are used in systems up to 50 ton capacity. The water flows through multiple coils which may have fins to increase the heat transfer coefficient. The refrigerant flows through the shell. However, in small capacity condensers, the refrigerant flows through the coil while water flows through the shell. When water flows through the coil, cleaning is done by circulating suitable chemicals through the coils. Let me show a picture of shell and coil type. So you can see the shell and coil type of condenser here. As you can see here, this is your shell. Okay, so refrigerant vapor enters at the top. It comes in contact with the coil. So this is your coil. Okay, through the coil the coolant flows. In this case, the coolant enters at the bottom and leaves from the top. So the coolant flows through the coil, and the refrigerant vapor comes in contact with the coil. As it comes in contact with the coil, it rejects heat to the coolant and it condenses, and condenses drains out, and you will find that the condenses gets collected at the bottom, okay, and finally it drains out from the bottom. Okay, since the coolant is entering at the bottom, there is a possibility of having some subcooling, because the coldest part of the coolant comes in contact with the refrigerant that is leaving the shell. So you can have some kind of a some amount of subcooling, okay, so which will improve the performance. As I said, if the refrigerant flow rate is small, then having the refrigerant on the shell side will not give you sufficient heat transfer coefficient. Okay, in such cases, when you have small refrigerant flow, the refrigerant will be on the coil side, whereas the coolant will be on the shell side. Okay. Now let us look at the third type, that is the shell and tube type condenser. This is the most common type of condenser, and it is used in capacities varying from 2 tons up to thousands of tons. In these condensers, the refrigerant flows through the shell while water flows through the tubes in single to 4 passes. The condensed refrigerant collects at the bottom of the shell. The coldest water contacts the liquid refrigerant, so that some subcooling can also be obtained. Let me show a picture of a typical shell and tube type of condenser. You can see here a shell and tube condenser with 2 tube passes. What is the meaning of tube passes? Let me explain the construction details. You have the outer shell here. Okay, so the refrigerant vapor which flows through the shell enters at the top, okay, and leaves from the bottom. And this shell consists of several tubes. Okay, so these are the tubes. You can see the coolant tubes, and through these coolant tubes, the coolant flows. In this kind of an arrangement, the coolant enters at the bottom, flows through all these tubes. Okay, since it is 2 tube pass, the coolant flows through the condenser twice. That means first it flows like this, and then from the end plate again it flows through the condenser. Okay, so that means it enters like this, and again it flows like this. So it crosses the refrigerant twice. So you call this as 2 tube pass type. of condenser. Okay. So, as the refrigerant vapor comes in contact with the coolant through which the coolant is flowing, again heat rejection from the refrigerant takes place. So, refrigerant condenses and the condensed refrigerant again collects at the bottom of the shell. Okay. And finally, this condensed refrigerant leaves from the bottom. Okay. Typically, whenever you are using shell and tube type of a condenser, this refrigerant goes to a receiver from where it goes to the expansion device. Since the coolant is again entering at the bottom and its temperature at the bottom is very less compared to the coolant leaving temperature, there is a possibility of some subcooling of the refrigerant. Okay, because the refrigerant leaving the condenser comes in contact with the coolant at the lowest temperature. Okay. Now, some heat rejection also takes place from the shell, and the shell also acts as a receiver. So, as I said, the heat rejection to the surroundings also takes place from the shell. So, shell is not insulated. The most common type of shell and tube type of condenser is of horizontal shell type, that means the orientation is horizontal. Of course, you can also have a vertical shell and tube type of condensers which are commonly used with ammonia in large capacity systems. So, the advantage of vertical shell and tube type of condensers is that since the water flows through the tubes and if the water quality is not very good, then after some time fouling occurs on the water side. Okay. So, the tubes require continuous cleaning. Okay. So, if the condenser is vertical, then without shutting down the plant you can clean the tubes from the top. Okay. So, this is the advantage of vertical shell and tube type of condenser which are normally used with ammonia. Okay. Now, let us look at evaporative condenser. In evaporative condensers, both air and water are used to extract heat from the condensing refrigerant. Evaporative condensers combine the features of a cooling tower and a water cooled condenser in a single unit. Water is sprayed from top part on a bank of tubes carrying the refrigerant, and air is induced upwards. There is a thin water film around the condenser tubes from which evaporative cooling takes place. So, now let me explain the working principle of evaporative condenser. This picture here shows a typical evaporative condenser. So, what you have here is refrigerant tubing. Okay. So, this is the refrigerant tubes. So, refrigerant enters these tubes and it flows through the tube and it leaves from the bottom. Okay. And this entire refrigerant tubing is kept in an outer let us say that an outer shell, and water is sprayed. You can see that water is sprayed onto these tubes, and when water is sprayed onto these tubes, a thin water film forms around the, let us say that this is your condenser tubing. So, outside the condenser tube a thin film of water forms. Okay. So, this is the film of water. Okay. And simultaneously some air is induced. You can see that at the top of the evaporative condenser you have air blowers which induce air flow. So, air is taken in from the bottom. Okay. So, air flows first over the refrigerant tubing, then it comes in contact with the water spray. So, when air comes in contact with water spray, there will be some evaporative cooling. That means, if the air is not saturated, then some water from the water spray evaporates. Okay. That means, you have the heat transfer both latent as well as sensible from the water. Okay. So, as a result the water temperature drops. So, the water finally that is coming onto the tube surface of the refrigerant has a temperature lower than that of the dry bulb temperature of air. Okay. It will, in fact, it will be closer to the wet bulb temperature of the air. Okay. So, you can see that since the water temperature, that means the film of water has a much lower temperature than the dry bulb temperature of air, the heat transfer will be very effective. Okay. Finally, the air leaves from the top, and you have drift eliminators which will prevent the exit of water droplets along with the air. Okay. So, the water droplets are arrested here and they fall back. So, water falls here is collected in the water sump, and again the same water is pumped to the top, and from the top you have nozzles from which the water is sprayed onto the refrigerant tubing. Okay. Whatever you do, there will be some amount of water loss here because of the evaporation of water. So you have to continuously supply some amount of makeup water. Okay, the makeup water is supplied to this tank or to the water sump using a float type of valve. Okay, so this is a typical evaporative condenser. Now the heat transfer coefficient for evaporative cooling is very large, because here the heat transfer takes place both sensibly as well as by latent heat transfer mode. Hence the refrigerant system can be operated at low condensing temperatures. Typically the condensing temperatures will be about 11 to 13 Kelvin above the wet bulb temperature of air. This is important. So this is the wet bulb temperature of air. And the role of air is primarily to increase the rate of evaporation of water. Okay, so heat transfer from refrigerant to air is not so very high, but the air primarily takes part in evaporative cooling of the water. Okay, and the required airflow rates are in the range of 350 to 500 meter cube per hour per ton of refrigeration. And these evaporative condensers are mainly used in medium to large capacity systems. And these are normally cheaper compared to water cooled condensers, which require a separate cooling tower. And evaporative condensers are used in places where water is scarce. This is because you will find that in evaporative condensers the water consumption is typically very low. That means about 5% of an equivalent water cooled condenser with a cooling tower. However, the disadvantage of evaporative condenser is that since condenser has to be kept outside, this type of condenser requires a longer length of refrigerant tubing, which calls for larger refrigerant inventory and higher pressure drop. So, this is a disadvantage. Okay. Now, let us compare air cooled condenser with water cooled condenser. Let us look at the salient features here. First, let us look at different parameters. For example, the temperature difference. Here the temperature difference is nothing but the condenser temperature, that means the temperature at which condensation is taking place minus the coolant temperature. Okay. So, you will find that in case of air cooled condensers, this temperature difference varies from 6 to 22 degrees centigrade, whereas in water cooled condenser this temperature difference varies between 6 to 12 degrees centigrade. That means you can operate the condenser of a water cooled condenser based refrigerant system at a lower temperature. Okay, because the required temperature difference between the coolant and the condenser is small. Okay. In addition to that, whenever we are using water as the external medium, you will always find that the temperature of the water is much smaller than the dry bulb temperature of the air. Okay, that means the external fluid temperature itself is smaller. As a result, you will find that compared to the air cooled condenser based system, the condenser of a water cooled condenser will be operating at much lower temperature. And as you know that if you operate the condenser at a lower temperature, the COP of the system will be higher. Okay. So, in the end you find that the air cooled condenser based systems will give much lower COP compared to a water cooled condenser based system. Okay. Next, if you look at the volume flow rate of coolant per ton of refrigeration, you will find that in air cooled condensers the volume flow rate of air per ton of refrigeration varies from 12 to 20 meter cube per minute, whereas it is very small, that means about 0.007 to 0.02 meter cube per minute in case of water cooled condenser. Why the volume flow rate of air is so large? Because of two reasons. The first reason is that the density of air is almost 1000 times less than that of water, right. The water density, if it is around 1000 kg per meter cube, the air density is around 1.2 kg per meter cube. Okay. So, its order of magnitude is about 1000 times. Okay. So, as a result, for a given mass flow rate, the volumetric flow rate will be very high if you are using air. In addition to that, the specific heat of air is typically 1/4 that of the specific heat of water. Okay. So, ultimately you will find that the rho into Cp of air is about 4000 times less than that of rho into Cp of water. As a result, the required volumetric flow rate of air will be much larger than that of the volumetric flow rate of water. Okay. Next important performance parameter is the heat transfer area per ton of refrigeration. You will find that in case of air cooled condenser, the heat transfer area per ton of refrigeration is about 10 to 15 meter square, whereas it is about 0.5 to 1 meter square in case of water cooled condenser. That means the required area is much larger in case of air cooled condenser compared to water cooled condenser. Again, what is the reason? The most important reason is that air is a bad conductor of heat compared to water. As a result, you find that the heat transfer coefficient that one can obtain with air is much smaller than that of water. Okay, since heat transfer coefficient is small, the overall heat transfer coefficient of the condenser will be small. As a result, the required area of the condenser will be much larger when you are using air cooled condenser. Okay. Next comes the phase velocity. The phase velocity of air cooled condenser varies from about 2.5 to 6 meter per second, whereas in case of water it is slightly smaller, it varies from about 2 to 3 meter per second. Finally, the fan or pump power per ton of refrigerant. This is a parasitic power, okay, required for circulating the external fluid. You find that in case of air cooled condenser you require about 75 to 100 watts per ton of refrigeration, whereas it is negligible in case of water cooled condenser. This is because of the reason that in the air cooled condenser the volumetric flow rate of air is much larger. Okay, so you have to, the fan or blower has to handle much larger volumetric flow rate of the fluid. As a result, the required power also will be high. Okay. Let us look at some of the advantages and disadvantages of air cooled and water cooled condensers. Compared to water cooled condensers, air cooled condensers are simple in construction. Disposal of air is not a problem and air is available in plenty, and fouling or scale deposition is small compared to water cooled condensers, and very little maintenance is required. So, these are the main advantages of air cooled condensers. However, there are certain disadvantages, as I have already discussed. Condenser temperature will be higher and COP will be less, and typically the cost of an air cooled condenser will be 2 to 3 times more than the water cooled condenser. Okay, so these are the disadvantages. That means initial cost will be high, and because of these reasons, use of air cooled condensers is normally restricted to 10 ton capacity, although the blower power goes up beyond 5 ton capacity. And in systems up to 3 ton capacity with open compressors, the compressors are mounted on the same chassis as the compressor, and the compressor motor drives the condenser fan also. As I said, the whole unit is available as a condensing unit, it is available off the shelf. And in Middle East countries where there is a shortage of fresh water, the air cooled condensers are used up to much higher capacity, that means up to 100 tons of refrigeration or even more. And water cooled condensers require a cooling tower, water treatment and maintenance. So, that is the reason why the initial cost of water cooled condenser based system is much higher than that of air cooled condenser based system. Okay. Now, let us look at the analysis of condensers. Typically, the total heat rejected in the condenser is given by QC is equal to m dot into H2 minus H4, which is equal to m dot subscript external Cp external into T external O minus T external I. Okay, let me show the cycle, so it will be easy to understand. As I mentioned, the heat rejection process in the condenser is from 0.2 to 4. Okay, so if you take the condenser, the refrigerant enters at state 2, okay, and it leaves at state 4. Okay, so this is the condenser, and the heat rejection rate is, let us say, QC, and if the refrigerant flow rate is m dot R, then if you take a control volume across the condenser and if you apply energy balance, and if you assume that kinetic and potential energies changes are negligible, then you can easily show that QC is nothing but m dot R into H2 minus H4. Okay. And from the external fluid side, let us say that this temperature, okay, of the external fluid is T external in, and this temperature, let us say that this is T external out, and let the flow rate of the external fluid be m dot external. Then QC is also equal to, okay, let me write here, QC is also equal to m dot external into Cp, some average Cp of the external fluid, into T external out minus T external in. Okay, so this is what is shown in this equation, right. And now QC can also be written as QC is equal to U into A into delta T subscript M, where delta T subscript M is the mean temperature difference, U is the overall heat transfer coefficient, and A is the required area. Now first let us look at what is known as condenser heat rejection ratio. What is condenser heat rejection ratio? The heat rejection ratio, or HRR, is the ratio of heat rejected to the heat absorbed. Okay, that means heat rejection rate in the condenser to the heat extraction rate in the evaporator, and you know that heat extraction rate in the evaporator is nothing but the refrigeration capacity. So the heat rejection rate can be written as heat rejection rate is equal to QC, heat rejection rate in the rate at which heat is rejected in the condenser, divided by the refrigeration capacity QE. Now from the overall energy balance of the refrigerant cycle, we can write QC as QE plus WC, where WC is nothing but the power input to the compressor. Okay. So finally heat rejection rate is QE plus WC by QE. This is equal to 1 plus 1 by COP, because this is nothing but 1 plus WC by QE, and WC by QE is nothing but 1 by COP. So finally you find that the heat rejection rate is a function of COP of the system. Okay, so if you know the COP, you can find out heat rejection rate, and if you know the heat rejection rate and refrigeration capacity of the system, then you can find out what is the rate at which heat is being rejected from the condenser, that is QC. Okay. Now since here heat rejection rate is a function of COP, it can easily be inferred that the heat rejection rate increases as evaporator temperature decreases and or condenser temperature increases. Okay, so let me show a typical performance curve. Okay, so this is a typical performance curve of a condensing unit. You can see here the heat rejection rate on the y axis and the condenser temperature on the x axis for different evaporator temperatures. For a given evaporator temperature, as you can see that as the condenser temperature increases, the heat rejection ratio increases, because we know that heat rejection ratio is equal to 1 plus 1 by COP. So as Tc increases, COP reduces, therefore heat rejection ratio increases as shown here. Similarly, at a given condenser temperature, as the evaporator temperature increases, COP as TE increases, you know that COP increases, as a result heat rejection ratio decreases. That is what is shown here. And compared to an open type of compressor, you can see that for the same condenser and evaporator temperatures, the heat rejection ratio of hermetic compressor is larger than that of an open type of compressor. Okay. Here the solid line is for open type compressor and the dashed line is for hermetic compressor. This is because the reason that you know that in a hermetic type of compressor, heat rejection also takes place from the motor as well as the compressor. Okay. So as a result, the total amount of heat to be rejected in the condenser will be higher than that of an open type of condenser. Okay. This is also the reason why the hermetic type of compressors based systems give you lower COP. Okay. So that is what is mentioned here. At a given TE and TC, the heat rejection ratio of hermetic compressor based systems is higher than that of open compressor based systems. Now let us define what is known as mean temperature difference, delta Tm. In refrigerant condensers, the mean temperature difference delta Tm varies along the length. Okay, so let me explain this. This shows the temperature profile versus length of a typical refrigerant condenser. Okay, so you have the refrigerant condenser here. So this is the solid line. This line is for the refrigerant temperature profile, whereas the dashed line is for the external fluid. Okay, so you can see here that the refrigerant temperature varies in the initially. Okay, so this, as you know, is nothing but your desuperheating zone. Okay, during this zone, the pressure remains constant but the temperature varies. Okay, then you have the second stage or second zone, the condensing zone. Okay, during the condensing zone, the temperature remains constant as long as the pressure remains constant, right. Then finally you may have a third zone which is known as your subcooling zone. Okay. Again, during the subcooling zone the pressure remains constant and the temperature varies. Okay. So, this is the temperature profile as far as the refrigerant is concerned. Now, the temperature of the external fluid varies in this direction. Of course, you get a linear variation if the specific heat of the external fluid does not vary much. So, you can get almost a linear temperature profile, and what I have shown here is a counter flow. That means external fluid is flowing in this direction and refrigerant is flowing in the opposite direction. Okay. So, the external fluid temperature, as you know, increases continuously as it flows through the condenser, right. Now, you can see that the temperature difference between the refrigerant and external fluid varies continuously. Okay. The temperature difference is nothing but at any point the temperature difference delta T is nothing but T refrigerant minus T external fluid, right. So, T refrigerant minus T external fluid varies continuously throughout the length of the condenser. Okay. So, if you want to define some kind of a mean temperature difference, it is a bit difficult here because of the continuous variation. So, what is done in normal for a rough estimation of the condenser area is that we neglect the desuperheating and subcooling zones, and we assume that the temperature of the refrigerant remains constant throughout the condenser and it stays at the condensing temperature corresponding to the condenser pressure. That means, the temperature inside the condenser is assumed to be at a value equal to the saturation temperature at the condensing pressure. Okay. That means, what we do here is we assume that the temperature remains constant at the condenser temperature value. Okay. That means, we neglect the temperature variation in the desuperheating region as well as in the subcooling region. So, as a result you find that under these assumptions the temperature profile will be something like that. The refrigerant temperature remains constant, okay, and it varies like this, and the external fluid temperature varies like this. Okay. So, the advantage of making this kind of simplification is that you can define what is known as a log mean temperature difference for the condenser if you make this type of an assumption. Now, how this type of assumption can be justified? Okay. Now, let us look at what happens during the desuperheating zone. During the desuperheating zone, you can see that the temperature difference between the external fluid and the refrigerant is typically large. Okay. That means, for the desuperheating zone, you find that delta T, which is nothing but T R minus T external, is large. Okay. Whereas, the heat transfer coefficient on the refrigerant side, that means HR, is nothing but heat transfer coefficient on the refrigerant side is small. Okay. Why heat transfer coefficient on the refrigerant is small? Because during the desuperheating process, the refrigerant does not undergo any phase change. Okay. That means, it is a sensible heat transfer process. Okay. So, that means, it is a single phase heat transfer process, and the heat transfer coefficient is because of the convective heat transfer coefficient due to the vapor flow. Okay. And vapor has lower thermal conductivity. So, you find that typically the heat transfer coefficient in this region, that means in the desuperheating region, is small compared to the condensing zone, because in the condensing zone the heat transfer is both by sensible as well as latent mean. So, you find that the condensation heat transfer coefficient is much larger than that of the single phase heat transfer coefficient. Okay. So, in the desuperheating zone, HR is small, whereas delta T is large. Okay. And if you look at the condensing zone, okay, in the condensing zone you find that means this zone. In this zone the temperature difference is typically small compared to this zone, that means delta T is small. Okay. Whereas, the refrigeration heat transfer coefficient during condensation is large, right. So, to summarize, during the desuperheating phase delta T is large and HR is small, and during condensation process delta T is small and HR is large. So, finally, we assume that, or if you calculate, you will find that the product HR into delta T, okay, is almost same, okay, for condensing as well as desuperheating zones, okay, condensing and desuperheating zones. Since HR into delta T is almost same, the area required will also be per watt of heat transfer, the area required will also be same. So, we justify saying that we can take a same temperature, that means we can neglect the desuperheating phase, and we can also assume that during this phase also the temperature remains constant, and the heat transfer coefficient during the desuperheating region is equal to the condensation heat transfer coefficient. Okay, so this is the simplification. Okay, and normally the heat transfer in the subcooling zone is typically small, so you can neglect that for rough estimation, right. So, during design all that we have to do is to find out the condensing heat transfer coefficient HR and assume the temperature to remain constant at the condensing temperature, okay, Tc, right. So, by this means you can eliminate the temperature variation during the desuperheating and subcooling regions, and you can have a constant temperature throughout the condenser length. Okay. So, this procedure is very simple and it gives a rough estimation of the required area of the condenser. Okay. But normally in commercial condenser designs and all, this is process is not used, and in those actual condenser design what is done is these three regions are these three regions are considered separately. Okay, that means the entire heat rejection process is divided into three separate regions, right. And these three separate regions, the required areas are calculated separately. That means for this region you find out what is the mean temperature difference and what is the heat transfer coefficient, and finally find out what is the area required, okay, for region 1. Similarly, for the condensation zone you find out what is the mean temperature difference and find out what is the condensation heat transfer coefficient on the refrigerant side, and again find out what is the area required for the condensation region. And similarly, for the subcooling region you find out what is the delta T mean, and you find out the heat transfer coefficient, single phase heat transfer coefficient, and again find out what is the heat transfer area required for subcooling, and the total area A total is nothing but A1 plus A2 plus A3. Okay. So, this procedure will give you the more accurate condenser area requirement, but as you can see that the process is quite complicated. Okay. Right. So, now based on these assumptions, we can define what is known as the log mean temperature difference, and this is given by log mean temperature difference is nothing but T external O minus T external I divided by natural log of Tc minus T external I minus divided by Tc minus T external O. Okay. So, this can also be defined like this. For example, if you have under the assumption of constant temperature, let us say that we are plotting length versus temperature. So, the condenser temperature remains constant at Tc, okay, whereas the external fluid temperature varies from T external into T external out. So, the log mean temperature difference, okay, LMTD is defined as the temperature difference at the inlet, let us say delta T at one end, okay, let me call it as and let us say end 1 and end 2. Okay, the log mean temperature difference is defined as delta T at end 2 minus delta T at end 1 divided by natural log of delta T2 minus delta T1. Okay. Now, what is delta T2? Delta T2 is nothing but Tc minus T external O, right, and delta T1 is nothing but the terminal temperature difference at end 1, this is nothing but Tc minus T external I. So, if you substitute this, the Tc gets cancelled here. So, finally, you will find that LMTD is nothing but T external O minus T external I divided by natural log of Tc. Of course, if you write in delta T2 minus delta T1, this becomes T external in minus T external out divided by Tc minus T external in divided by Tc minus T external, I am sorry, T external out divided by Tc minus T external in. Okay. That is what is shown here. Of course, here there is a slight this thing. Here it is defined in terms of delta T at terminal 1 minus delta T at terminal 2 divided by ln at delta T 1 divided by delta T 2. It does not make any difference whether you can show it as a difference between terminal 1 minus terminal 2 divided by natural log of terminal 1 by divided by terminal 2, or terminal 2 minus terminal 1 divided by natural log of terminal 2 divided by terminal 1. Okay, the final value will be same, right. So, if you know the condenser temperature, okay, that is Tc, and if you know the inlet temperature of the external fluid, and from the energy balance and mass flow rate of the external fluid, if you know what is the outlet temperature of the external fluid, then we can calculate what is the log mean temperature difference of the condenser. Okay. Once you know the log mean temperature difference of the condenser, and if you also know the heat rejection rate in the condenser, and if you can evaluate the overall heat transfer coefficient, then the required area of the condenser can be obtained. Okay. So, remember that this is a simplified procedure, and this procedure is normally used for a rough evaluation of the required area of the condenser. Okay. In the next lecture, we shall see how to evaluate the overall heat transfer coefficient of the condenser. Okay. And since we know the QC from heat rejection ratio and QE, we can calculate the required area. Okay. So, let me summarize what we have learned in this lesson. In this lecture, the following topics are discussed: classification of refrigerant condensers based on external fluid, based on the construction, etc., and salient features of different types of condensers, and we have also seen the comparison between air cooled and water cooled condensers, and the typical advantages and disadvantages of each of these condensers, and we have also discussed evaporative condensers. And then we have defined heat rejection ratio as a function of COP of the system, and then we have discussed the calculation of log mean temperature difference and typical assumptions made in calculating the log mean temperature difference of the condensers. Okay. And as I already mentioned, in the next lecture we shall see the calculation of the heat transfer coefficients on the external fluid side, heat transfer coefficients on the refrigerant side, and finally how to calculate the overall heat transfer coefficient of each of these condensers, and from the overall heat transfer coefficient how to calculate the required area of the condensers. Okay. Thank you. Welcome back. The specific objectives of this particular lecture are to present expressions for overall heat transfer coefficient, present expressions for various heat transfer areas in plate fin type air cooled condensers, present typical correlations for heat transfer coefficients on air side, water side, and condensation heat transfer coefficient, and discuss effects of non-condensable gases. At the end of the lecture, you should be able to estimate the overall heat transfer coefficient values for heat exchangers with and without fins, calculate various heat transfer areas in plate fin type air cooled condensers, use various correlations and estimate heat transfer coefficients on external fluid side and on condensing refrigerant side, and discuss effects of non-condensable gases. So, let me give a let us look at a typical design problem. Normally in any design problem, the inputs are the operating temperatures, that means the evaporator temperature, condenser temperature, etc., refrigeration capacity QE, the heat rejection ratio HRR, mass flow rate and inlet temperature of external fluid, that is M external, and T subscript external I. Okay. Normally these values are available in any typical design problem. And what is the objective of the design problem? Objective is to find out the area required, that is we have to find out A, and the equations available are like this. First equation is like we have seen in the last class, that the heat rejection rate in the condenser QC is given by QC is equal to heat rejection ratio HRR into refrigeration capacity QE. So, we know both HRR as well as QE because they are given as input. So, from this equation we can calculate what is the total heat transfer rate at the condenser. Okay, so, this is the first equation one should use. We can also write the heat rejection rate at the condenser in terms of the external fluid. That means we can write QC is equal to MCP of external fluid into T external out minus T external in, right. In this equation we you can see that we know M external, that means the mass flow rate of the external fluid is known to us and the inlet temperature of the external fluid is known to us. So, from this we can calculate what is the outlet temperature of the external fluid since QC is known to us. The third equation that we will be using is the expression for log mean temperature difference. This is defined in the last lecture. This is defined in terms of the fluid inlet and outlet temperatures and the condensing temperature. Since we know all these temperatures, we can calculate what is the log mean temperature difference. Finally, what we do is we use this equation, that is QC is equal to U into A into LMTD. In this equation, QC is known to us, LMTD is known to us, and we have to find out A. So, for what we have to do is we have to somehow estimate the overall heat transfer coefficient U. So, that using this one equation we can calculate what is the area required, right. So, this is the general procedure to be followed in the design of any heat exchangers, not necessarily the condenser. Okay. From the given input we have to find out the mean temperature difference and then we have to find out what is the overall heat transfer coefficient. Okay. Once we know the overall heat transfer coefficient, then we can find out the area required. These kind of problems are known as design problems. Okay. So, the objective is to find or design the heat exchanger or to find out the area required. There are other types of problems known as rating problems in which the area is given, okay, and we have to find out what is the heat transfer rate. Okay. So, in this particular lecture I am confining myself to the design problem, typical design problem, how to estimate the area. Okay. So, first as I have already mentioned, in order to estimate the area we have to first find out what is the overall heat transfer coefficient U. So, evaluation of U is an important step in the design of a condenser. The overall heat transfer coefficient can be based either on internal area AI or external area AO of the condenser. Okay, and in general we can write the product UA, that is equal to UIAI, which is equal to UOAO, which is nothing but 1 by summation of Ri, okay, from I is 1 to n, where Ri is nothing but the heat transfer resistance of the ith component. Okay. Now, a general expression for overall heat transfer coefficient of a finned heat exchanger is given by this expression. As I have already explained to you, this is the overall heat transfer coefficient, that means UA. Okay. This depends upon your different resistances which are in series. So, for any general heat exchanger there are 5 resistances here. Okay. For example, the first resistance, this resistance accounts for the convective resistance of the outer surface, that means that is why the subscript O is there, okay, of a finned heat exchanger. So, this is the convective heat transfer resistance of the outer finned surface, that is resistance 1. Then you have second resistance, this is nothing but the conductive resistance offered by the wall of the heat exchanger or wall of the condenser. Then the third resistance,